everyone, so I want to continue our discussion with circular motion and do a few more practice questions. Alright, so pause video, work itself, and we'll go over in a second. Alright, so here they talk about the apparent weight. If you recall in the previous video or previous unit, I mentioned that the apparent weight is the normal force. Again, they're basically hinting that they want us to find the centripetal force, since a person on the outer wall will end up having their normal force acting as the centripetal force. So I set the normal force equal to centripetal force, plug in my numbers, and end up getting 180 newtons. So this person who would normally weigh 500 newtons on Earth will end up feeling about I guess a little bit more than a fifth of their normal weight being on here. All right, so here's another part to the same question. So pause the video, work itself. I'm going in a second. Now, for this, there's a few different ways to do this. I haven't actually gone into detail with the special method that I have to approach these types of questions. So you can do a variety of different things. You can redo the calculations, but this time change the speed to 24 meters per second, and then figure out what the new acceleration would be. Uh, you can do a proportion where you divide the two equations, leaving only what's left. I'm going to go a little bit simpler um, for this. So what I'm going to do is because they're talking about how the speeds affecting centripetal acceleration, I'm going to start with the centripetal acceleration equation. Now, they don't say anything about the distance or the radius changing, so I'm actually going to get rid of that, and I'm going to rewrite this so that its AC is proportional to v squared. Remember, this is a way that we can write the relationship between two terms. Because there's a square on here, this is telling me that there's an exponential relationship between velocity and acceleration. If whatever I plug into here, if I square it, that's how the acceleration is going to change. So in this case, they say that the velocity is doubled. So when I plug that in, 2 for velocity, because that's being doubled, because of the square, that means that doubling the velocity will quadruple the centripetal acceleration. So this is my method of doing it. If you don't like it, you don't have to do it. There's a variety of different ways of going about this. One thing to note though is that some of the questions that would have you do something like this, they might not give you any numbers to begin with, so you wouldn't really be able to do a calculation. But in that case, what you could do is just make up the numbers. Do maybe the first set of calculations where everything's a 1, and then do the second calculation where you end up changing the measurement that they mentioned, like in this case, velocity, and then see what you get and compare them. All right. So here's the next question. Pause the video, work itself. I'm going to go in a second. All right. So for this, what we're going to do is find the acceleration by plugging the numbers into our centripetal acceleration equation. Pretty straightforward. They give us all the numbers. We end up getting the centripetal acceleration's 4. Then what I can do for part B, they want us to find the force. So again, I have this acceleration. I basically put it into the net force equation, multiply the acceleration by 0.5 to get that it is 2 newtons. And then at the end, they want to know what specific force is acting on this mass to keep this in the circular motion. They mentioned that it's being swung by a string, so that is a tension force. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So here they want us to determine the centripetal acceleration on the car. What I can do is I plug it into my general equation, and I end up getting that the centripetal acceleration is about 78.1 meters per second squared. Just like in the last setup, finding the frictional force, again, the frictional force is my centripetal force. There's really no way for me to use mu Fn, so I'd have to go this route. Take that acceleration, multiply it by the 1500, and end up getting that the frictional force is pretty much 1.17 times 10 to the 5th newton, so a very large number. To find the minimum coefficient of friction needed for between the tires and the road to keep this circular motion, I'd have to take the equation, friction is less than or equal to mu Fn, plug my numbers in. Because I'm on a flat horizontal surface, Fn is going to be equal to my Fg, so it's just 1500 times 10. End up getting that mu would have to be greater than or equal to 7.81, you know, value. Um, One thing to note is most of the coefficients that we deal with are usually less than one. It doesn't mean that it's impossible for the coefficient to be greater than one. It just means that it's an extremely sticky case. So in this case, this would be a very sticky, almost like glue or tape being required for the car to actually make this turn. So what this really means is that the likelihood of a car actually making the turn at this speed, at that very short radius, is very unlikely. All right, so in this next set, there's about not four, sorry, there's six problems where it's basically doing the same thing, just changing the coefficient of friction. So work on this. My big recommendation, though, is solve the question in variable terms first. That way, all you have to do is just change the values. All right, so pause the video, work itself, and we'll go over in a second. All right, now, again, this is pretty much the same problem as last time. So again, it's a car going around a turn. What I can do is set the frictional force equal to the centripetal force. I know that the frictional force, because it's acting centripetally, it's going to be equal to mv squared over r, and I know that the normal force is equal to the mg, the weight. So I end up having this mu mg equals mv squared over r. The masses drop, and then moving everything over to one side, I end up getting this. You can see for yourself. Again, this is like the work that I got from the last problem, which is why I'm not really going into much detail with it. So what I can do now is just plug my numbers in, um, and I end up getting that the maximum speed that a car can actually drive around this specific turn is 11.62 meters per second. Now, one thing to note is that right now, according to this problem, mass doesn't matter. And that actually is kind of true. In a real case, the mass of the car wouldn't affect how fast you are or aren't allowed to make a turn. It does play a part, though, in the stability issue. One thing that we'll see in one of the later units called rotation, that typically cars that are heavier tend to be bigger, and in most case, taller, I should say. And because of that, when you make the turn, it can result in the car being a little bit more unstable and causing it to tilt more and having the likelihood of it tipping over. However, while that aspect would play a factor as far as like mass related to being able to make a turn, the mass doesn't actually affect whether or not the wheels themselves can withstand the turning. So I just want to clarify that. All right, so for part B, I can use the same equation and just change the number for mu to zero point 0.6, and we can see, which makes sense that as this coefficient drops, the value drops. So it goes from a little bit over 11.6 to a little bit under 9.5. So that is a decent drop in my maximum speed just by having the concrete wet. So again, a perfect example of why it's important that when the weather gets bad and it starts raining, you don't want to keep driving like you would normally drive. Especially since I don't really know how wet this concrete is, but if there are large puddles, I'm pretty sure this coefficient would probably be a lot less as well. All right, so keep going with this. Pause the video, work itself, and I'm going for a second. All right, like I said, pretty much jumping straight into it, we have the same starting equation, change the coefficient, and we get pretty much a similar answer that we got to part A. And part D is also very similar. Again, we're changing the concrete to asphalt. It does make sense again that it's a little bit lower. If you've ever seen asphalt, it is smoother than concrete. So it does make sense that these numbers are going to be smaller. So we'll just move on to the next part. which is these last two. So pause video, work self, and go in a second. All right, so the second case of bad weather conditions that you might experience is where the road is covered with ice. So, again, to kind of reiterate how important it is that you make turns consciously and are aware of the weather conditions, if we plug in this new coefficient in for mu, we end up getting that the max speed drops significantly to about 5.5 meters per second. So what this means is that in the previous case, section A, the max speed was about 11.6, which is roughly about 25 miles per hour. Now, by introducing ice onto that road, my maximum speed drops to 5.5 meters per second, almost a little bit, about like a half of the original value, a little bit more than a half. And that would be equivalent to, I think, about 11 miles an hour. So, yeah, we end up dropping our max speed by half just by introducing ice. So again, extremely important that you make sure that you're aware of your weather conditions before you make any turns, especially if you're going to make a fast turn. Teflon and Teflon, obviously you would never actually experience this, but this is one of the main materials that we have that is essentially frictionless. So if we had these two materials rubbing against each other, it turns out that the max speed we'd be able to make in order to make the turn would be about 2.74 meters per second. So again, not that fast. All right. So here's next question. Pause video, work self, and go in a second. All right. So the first part is to draw an FBD. So I want to go through all the forces specifically. So we know that the gravitational force is pulling down. Now, normally we have a normal force going up, but now the surface is actually right here. Notice I didn't draw the ground. For those who don't know, the gravitron is basically a room that you go into. The room starts to spin, and you get pushed up against the wall, and then the wall ends up sliding up so that you're no longer touching the floor. So the only surface that you are physically in contact with is the wall. So the wall is the only thing that provides a normal force, and it always points perpendicular to the surface. So it's going to point to the left. And then the other thing to remember is that when you're up against this wall, you're not sliding down. The floor is underneath you, and you're stuck on the wall, which means that there has to be a force going upwards. And the only force that can keep you there is friction. So this is what the FBD will look like. Note that there is no force pointed to the right. Again, I am accelerating in this case. There's no need and no reason for there to be a force pointed to the right. To find the centripetal acceleration, I actually first have to figure out what the speed is, since I don't have enough information for that. So what I'm going to do is I'm going to find the circumference by doing 2 pi r. Now, the period is a little bit tricky to think about. Uh, like I said, I haven't really gone into too much detail with finding period, but the way we're supposed to do it here is that we're supposed to take the time and divide it by the number of rotations. Because remember, period is just a fancy form of time. So if I make 24 turns in 1 minute, what I can say is that I do 60 seconds. Within the 60 seconds, I can make 24 rotations. And if I do that math really quickly, this actually ends up being a period of about 2.5 seconds. So every 2.5 seconds, I go around the circle once. And you can check to make sure that after 24 turns, 60 seconds would have passed. So I can plug that in, and I end up getting that the speed of the student is, at max at least, 17.6 meters per second. Using this, I can plug it into the centripetal acceleration equation, plug the numbers in, and we get 44.2 meters per second squared. So this is actually pretty fast. This is about, I guess we could say, about 4.5 times the acceleration of gravity. All right, here are the next 3 parts. So pause video, work self, and we'll go over in a second. All right, so part C wants us to find the normal force acting on the person. If we look back at the FBD, we could see that the normal force is what's actually causing that circular motion. Again, without the wall, it's the person's not going to maintain circular motion. So I can just set the normal force equal to the centripetal force, MAC. Take the mass, take the acceleration that I just found, and I get that the normal force acting on the person is about 3,500 newtons. To find the frictional force, again, you might think that we can use mu Fn, but we don't have the coefficient. And in fact, the next question asks about the coefficient. So that means I have to use the FBD and go back to using Newton's laws. Because the frictional force is being balanced by the gravitational, I know that they should be equal. Again, I'm not sliding up or down, so the sum of the forces in the y direction should equal 0, meaning friction equals gravitational force. So the frictional force should be 800 newtons. With these two answers, I can now find the minimum coefficient by doing FF equals mu Fn, or less than or equal to mu Fn. Plug my numbers in, and I end up getting that the coefficient would have to be greater than 0.23, which honestly isn't too tough. If you recall in the previous problems, about zero point 0.2 for a coefficient is the equivalent or the slipperiness of rubber on ice. So that's kind of a not really rough surface. So as long as they make sure that the people aren't wearing something very slippery, most people are probably going to stick up against this wall without any problems. All right, and this will be the last question. Now, this one actually is tougher, at least at the very end. So, just pay attention and, stay focused. Um, Pause video, work stuff, and we'll go over a second. All right. So the first part's actually super easy. Calculate the weight of the watch. Fg equals mg. Plug the numbers in. We get 50 newtons. Easy enough. The next part says what's the vertical component. Now, I should have drawn an FBD. I didn't do it on here, but the FBD will look something like this. So this would be the vertical component of the wire. This will be the horizontal component, and this will be equal to Fg. So once again, since all the acceleration is acting horizontally, in the vertical direction, the sum of the forces should equal 0. So the vertical tension the vertical component of the tension should be equal to the weight of the object. So I just get it's equal to 50. So those two parts weren't tough. And these two parts actually won't be that tough either. So pause video, work self, and we'll go over in a second. All right, so part C wants to know what's the tension in the string. Now, we have to end up using our trig functions. So once again, I'm going to try to draw this a little bit. So the tension in the string acts along the string. I know the vertical component of the string. So I'm going to actually draw my arrow right here. So this is the vertical component. Well, I know that because of this angle of 30 degrees, I can use SOHCAHTOA to find this relationship. So what I can do is set FTY equal to the FT cosine theta. Again, because it's adjacent over hypotenuse. Plug my numbers in and end up getting 57.7 newtons. It's important to pay attention. Most of you probably would automatically do FTY equals to FT sine theta, but just be aware of where this angle is. If it's next to the vertical, then the sine and cosine gets flipped. Right? So that kind of leads into part D, where they want the horizontal component. So again, this is the horizontal component right here. And just as I said before, the cosine and sine flip. Normally, if the angle was to the horizontal component would be related to cosine. So this time it's going to be related to sine. Plug the numbers in that I just found. End up getting that the x component should be 28.9 newtons. So far, so good. Now, the next two parts are where it gets a little bit trickier. So pause video, work yourself, and we'll go over in a second. Alright, so part E wants to know what is the speed of the watch's rotation. Now, in order to figure out the speed, since I know that the x component is going to be equal to the centripetal force, I'm going to need to know what the radius is. So this is what I'm going to end up doing. I'm going to set the what I just got in part D equal to mv squared over r. Now I know what the mass is and I know what the velocity is from the and I'm looking for the velocity. The problem is r. Now you might automatically put zero point 0.5 meters as the radius, but that's not the radius of the circle. The zero point 0.5 is represented by this length here. The radius of the circle has to be this distance here because again this is the circle right here, so this is my radius. Looking at this, I can now see that I can use trig again, SOHCAHTOA, to find that the radius is going to be equal to zero point 0.5 times sine of 30, or it'll end up being 0.25. No, I left it as zero point 0.5 sine 30 just to kind of keep reminding it. So if I plug the numbers in and I make sure that I'm using the correct radius, I end up getting that the speed is 1.2 meters per second. Once I have that, I can find the period of rotation fairly easily. Again, I have to be aware that the radius is still different, but right there, it ends up being a simple plug and chug of 1.31 seconds. All right, so that was pretty much all the questions. Honestly, 13 is probably one of the tougher horizontal circular motion. There is actually one more question that's even tougher, but we're not really going to go over it. It's called a bank curve. So cars that are moving essentially on an inclined plane in a circular motion, those are extremely dirty. So I'm not going to go over them. But if you're interested, feel free to look at it. I so I don't think I mentioned this in detail last time, but I just want to quickly go over this. So we've talked already about what happens if the force, or since force and acceleration point in the same direction, I can say acceleration and velocity are either parallel or anti-parallel to each other. If this happens, we end up getting a case where the velocity or the magnitude of the velocity of the speed will change. In this case, I'd end up having the speed decreasing. If instead I had the velocity and the acceleration or the force in the same direction, then this would mean that the velocity would start to increase. But it would always maintain that same direction, or at least within the plane direction. In the case where I have it perfectly perpendicular like this, then what I'll have is a change in direction. Instead of but the value of the speed doesn't change. So if this was 5 meters per second, it's going to stay 5 meters per second, but it's going to rotate in a circle. And based off of the direction that the forces and the velocity is going, this would end up going in a counterclockwise direction. The way that you figure it out is, since the force is pointed upwards, that means that my center of the circle should be right here. Since this has to be located on the outer edge of the circle, that means my circle has to look like this. And because my velocity is pointed this way, I can already see that I have to go this way. All right, so easy enough. Now, I don't have a part for this. Oh, I don't have a part for this, but what you can now do is, using this understanding of these two things, I can give you a scenario where my velocity is pointed this way and my force could be pointed this way. And my question would be, what's going on to the velocity at this moment? So what you would do is you would break up the force into components. So since the force is going down and to the left, I have a leftward component and a downward component. And using these two things individually, I can compare to what I have here and see what happens. This horizontal component is opposite velocity, so the velocity will end up decreasing. And because of the perpendicular component kind of pointed downwards, I know that the center of the circle is going to be right here. The circle is going to be drawn like that. So it will be slowing down in a clockwise, I wrote clockwise direction. So it's going to go clockwise in a circle and decreasing in speed. you wouldn't really know what exactly the path would be without more information about what's going on with the force. If it's constant, or if it was just in that direction for that moment, and that it would change as it moves. I don't think you would see that type of question. Normally, the question kind of sticks with only at that specific moment. All right. So I want to move on to one of the last things, and that's the applications. So one of the main goals, or one of the main draws to circular motion, is that it allows us to get very high accelerations and forces in a very small area with not that much energy. If we weren't able to use circular motion and instead had to stick with just straight line acceleration, it would require rockets to actually get us to even relatively high accelerations. And in those cases, we wouldn't really be able to sustain it for that long. And it requires a very long track of land. So it's a lot of materials, very expensive, and not really worthwhile. But circular motion can kind of condense very high accelerations in a very small area, and we can use it in a variety of different things. Uh, Most common example that we all experience are dryers or washer machines too. If you've ever wondered, there's all those holes in the canisters, the bins. What ends up happening is the dryer and the washer both spin the clothes really fast to try to get a bulk of the water molecules off of your clothes. So it kind of flies into into those little holes. So it uses the aspect of circular motion to kind of fling the water off your clothes to kind of dry them. Centrifuges. So anyone who's done work in a science lab, or maybe in the medical field, know that there's this box called a centrifuge. You put samples in there. Typically, it's very commonly blood samples. And what it will do is it will spin the vials so quickly that it will separate everything by density. So you can kind of separate blood into all the different components. And another thing that circular motion is used for is high G training. So astronauts and fighter pilots, they need to be able to withstand high accelerations without passing out. So they'll go into basically these very large centrifuges, or very large gravitrons, that can spin at variable speeds in order to get used to this high acceleration so that they can fly without passing out. There's a bunch of videos that you can look up online where people are experiencing this. It is partially funny, but at the same time, interesting to see some of the effects. I highly recommend that you look it up. You'll notice that a lot of the people end up having faces that almost seem very sunken in, and that's because of the fact that the skin is actually starting to pull away from the face. So it's because of the again, the circular motion. And then there's also these two websites that are kind of interesting. They're the human limits and basically a magnitude of G forces. So if you recall in one of the questions that I did, I actually said that 44 meters per second squared was about 4.5 Gs. A G is related to the acceleration of gravity. So 10 Gs would be 10 times Earth's gravity. 100 Gs would be 100 times Earth's gravity, yada, yada, yada. So you can actually follow this link, and it will tell you all these very interesting things and how many G's there is. Like, for example, how many G's are in a car crash? How many G's are in a baseball bat? Like, swinging a baseball bat and you hit something, or kicking a soccer ball. What are some scenarios that have very high G's? What are scenarios that have very low G's? Roller coaster rides. What are the typical G forces on there? So I definitely recommend looking that up. It is kind of interesting. That's pretty much it. So there's a few more topics that I need to discuss in this unit. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.